Hi class, welcome to Unit 4, Lesson 6, where we look at color and wavelength. Today's learning goal, you'll be able to demonstrate understanding of color, wavelength, and dispersion. Success criteria for today is you'll be able to describe in detail color, wavelength, and dispersion. If you can identify the variation of index of refraction with wavelength, solve problems related to wavelength, and apply learning to daily life problems. First, let's talk about dispersion. Dispersion is when white light passes through a glass prism and different wavelengths are refracted through different angles, generating a display of spectral colors. This phenomenon is known as dispersion. On passing through a prism, white light is dispersed, broken up into its components to form the spectrum. Each of the colors bends by a different amount and emerges from the prism at its own distinctive angle. So we get the spectral colors display. So the index of refraction for a material usually decreases with increasing wavelength. And so, as you can see, as wavelength increases this way, we see this decreasing function in index of refraction. It goes down as the wavelength increases. And so in practice, this means that violet light refracts more than red light when passing from air into a material, because violet light is on this side of it has a higher index of refraction because it has a shorter wavelength versus that of red light, which has a larger wavelength and so smaller index of refraction. So in the prism, the amount the ray is bent away from its original direction is called the angle of deviation, represented with delta. Since all of the colors have different angles of deviation, they will spread out into that spectrum we saw because of the different the wavelengths, because each one has a different index of refraction. And so violet deviates the most, whereas red deviates the least, as we mentioned. And so you get a much greater value for delta of, or blue. Blue would just be a step down from violet, the second most deviating. And you just notice that how much smaller the angle of deviation delta R for red is than that of delta B, which happens because of this phenomenon we talked about here. And so to measure this type of stuff, we have something called a prism spectrometer, and it's a device that uses a prism to cause the wavelengths to separate. So you have the source come into its opening, and then you get this prism effect that splits, just like we saw the dispersion here, into the different colors, and then they can be viewed by the viewer through a telescope part of the device, so we can see the color separation. This instrument is used practically to study wavelengths emitted by light sources, as well as looking at the individual wavelengths and of the colors in the spectrum. And so when we have them broken up into its spectral lines, we can determine, it's used to determine the composition of material from based on the pattern of the spectral lines when it's in the colors. So let's do a problem. Red light with a wavelength of 6.5 times 10 squared nanometers travels from air into crown glass, N2 equals 1.52. And so we want to find the speed in the glass. So this is similar to our problems involving Snell's law from one medium to the other. And so remember that Snell's law was N2 over N1 equals to V1 V2, also equal to sine theta 1 sine theta 2 And we also said that it was also equal to lambda 1 over that of lambda 2. So remember, we had our n2 and n1 were the one that was opposite everything, and everything else was 1s on the top, 2 on the bottom, or flipped. You could do the other way, just the n's were the one that was the opposite. So when we look at red light, we got our wavelength here. So let's say that glass is 2s, air is 1, right? Because from usually the first one from air into crown glass. So that makes this lambda 1. And then we're given crown glass as an n value of 1.52, so we're going to say that's n2. From that chart, we know we've been using n1 equals 1.00 for air from that list of refractive indices from a few lessons ago. And we want to find V in the glass, so that's 2. So we have our lambda 1, n2, v2, n1, and since we're working with light, we can say that the speed of light we know is equal to c. So we can say the speed in air, which is 1, is 3.0 times 10 8, because that's in air. We don't know it in glass. In fact, we want to find it in glass, so that is our V2 in glass. So using our Snell's law, we don't have angles, we don't have enough wavelengths, we do have 2 speeds, and we have a refractive index, and so 2 refractive indices and 1 speed. And so we use this portion of the Snell's law, so we don't have to use all of it, and we solve for V2, our given, are required, what we were asked for, and we find it's equal to n1 over n2 times v1. We plug in our values, and again we only have 1 unit that keeps consistent, so our answer comes out to meters per second, and when we do the math, it's 1.97 times 10 to the 8th meters per second. And so we can say the velocity of this red light in the glass is this velocity. And the next part, what is the wavelength in the glass? So if you look at our convention, it's 2. Let's keep it consistent. So we're looking for lambda 2. And so we look at our Snell's law again. We now want to use the angles, and we have 2 speeds. We just calculated V2, and we were given V1. And so if we use these 2 parts of Snell's law, velocity and the speed and the wavelength, we look at this, and if we look for lambda 2, the one we're asked to find it equal to V2 over V1, lambda 1. We plug in our values, we see our units of meters per second cancel each other out, and we're left with whatever lambda 1 is in, and it's in nanometers. And so when we do the math, we find the answer is 4.28 times 10 squared nanometers. Again, if you converted your lambda 1 to something, it would just turn into that unit. And so we say the wavelength of the red light in the crown glass is 4.28 times 10 squared nanometers. And just a note, if you use Snell's law, since we had our refractive indices and we want to find the lambdas, since this is all equal, we could just use the lambda 1 over lambda 2 equals n2 over n1 and solve for lambda 2 and just plug in the n's, these n's, and you would get the same answer. So that is also correct that direction if you want to use the n's instead. And so that's it for today.